Good day, madam. My name is Dilanta Herat. My index number is 258776U. In this video, I will walk through my big data analytics assignment, part A, which I analyzed US flight delay and cancellation data from 2019 to 2023 using Apache PySpark on a Google Colab. And I use a dataset from Kaggle. This is my dataset, flight delay and cancellation dataset. Then the notebook covers five main areas: loading and inspection data, cleaning and pre-processing, page engineering, and exploratory data analysis, and final building machine learning model to predict the flight delays. So I uploaded that CSV file here. This dataset has 3 million data. Yep. So in the first cell, I set up my environment. Then the second one, I set up my Spark session. Here, one thing to note, once you set up this JDK, you have to restart the session and then run the PySpark cell. Otherwise, it will give some error. Then let's come to data loading part. Here, I loaded the flight CSV file into Spark data frame, and I use infer schema equal to true. So the Spark automatically detects column data types without me manually defining a schema. So this is acceptable for one-time load. The output shows the total number of rows and that the full schema. These are the column names with their types. Then this is the sample data for first five. And the next one, I describe the statistic, the usual things. Then I'm checking the null values for each column, the percentage values. In the next one, okay, we'll go to data cleaning and pre-processing. So this is the main cleaning cell. What I did, I casted the flight date to some proper date type. Then I cast all numeric delays and disturb columns to double to ensure that consistent arithmetic values. I separate cancel flight into their own data frame for cancellation specific analysis, and I filtered the main data frame to keep only non-cancelled, non-diverted flights. Then I can drop rows with nulls in the four essential columns. So the four essential columns are departure delay, arrival delay, distance, and airtime. So I drop that thing. Then fill null delay with zeros. And finally, I removed extreme outliers. The flight with delay outside the range of minus 120 to 1440 minutes, which are almost certainly data errors. So the output shows final count of clean flight records and cancel records. Okay, next cell about feature engineering. Here I created new features from existing columns that will be useful for both analysis and machine learning. And I extracted year, month, day of week, then day of month from the flight date. I extracted schedule, departure, hour from 4-digit time integer. I then classify each flight into time of day bucket: morning, afternoon, evening, or night. Likewise, I created them. Then I created binary target label called is delay, which if the arrival delay is 15 minutes or more, then it is considered as delay. Actually, that thing I took it from FAA's official definition. So I also categorize flight by distance into short, medium, and long, and calculate total delay cost column by summing of all 5 delay cost columns. So the sample output is something like this. Then I set up matplotlib seaborn panda for exploratory data analysis. In the puzzle, uh, here I'm plotting distribution of arrival delays. This histogram shows how arrival delays are distributed across all flights. Here, even though dataset has 3 million records, I only used 5% of the data to bring into pandas for plotting. Otherwise, it will freeze my view. The red dashed line marks the 15-minute delay threshold, and the green line marks 0. So these are non-delay flights. As expected, distribution is right is good. Most flights arrive on time, slightly earlier, but there are long tail of severe delays existing, as you can see here. Then next plot is about year-over-year flight performance. These two bars and line chart show year-over-year flight performance from 2019 to 2023. The left chart shows the percentage of delayed flight per year, and the right one shows the average arrival delay in minutes. The key observation here is that 2020 had significant fewer flights due to COVID-19, and then 2022-2023 shows the highest delay rates, likely driven by the post-pandemic demand surge. After COVID-19, there was a surge of travels. Then next plot about it's a bar chart, shows that delay rate broken down by month across year combined. So I highlighted the top quartile months in red. The pattern clearly shows that summer, which is June, July, they have highest delay rates. Then in December again, uh, this is coming due to the weather disruptions, because this data set coming from United States. Then the next one, delay rate by day of week. As name suggests, the delay rate for each day of the week. That highest delay rates due to the peak business and leisure travel volume converging on the same day on Fridays. So this one is having the highest one. And the next one, this dual axis chart shows both the delay rate and the total flight count for each scheduled departure hour. Bars represent the delay percentage in blue, and the red line shows flight volume. So early morning flights between 5 to 7 have the lowest delay rates, and delay compound through day as aircraft crew gate resource accumulate backlogs, begin in the evening between 6 and 9. Then okay, this is for airline delay rates. PSA, Noya, these are having less delays, and the worst performers are JetBlue's Frontier Airline, this Allegiant Air. They are the worst airlines. And this pie chart breakdowns total delay minutes by root causes like carrier, weather, the security, aircraft, things like that. This one, flight cancellation analysis. These two charts analyze flight cancellation. The left part shows the cancellation rate per year. I think data didn't come for some reason. I think it's outside of my data. But the right one, distribution of cancellation reasons. As previously I showed in the pie chart, the carrier, the how many records are delayed because of carrier, because of security. Okay, the most delayed factor is weather. Okay, then this one, the busiest route. The bubble scatter chart shows the relationship between route volume and delay rate, with the bubble size and color representing average arrival delay. So I annotate the top 10 busiest route. This chart is good example of using Spark's distribute aggregation to summarize millions of flight record by route and then visualizing the result. Then the last one, delay rate by flight distance. This bar chart shows the delay rate across short, medium, and long haul flights. Medium distance flight, they more tend to have the highest delay rate, and shorts are having less delays, the usual things. Then I will explain this machine learning part. I imported Spark machine learning lib components, string indexer, one hot encoder, vector assembler, standard scaler, and the random forest classifier. I select the feature columns as 4 categorical ones: airline code, time of day, distance category, season, and the numerical one, departure hour, month, day of week, distance, and schedule elapsed time, departure of delay. The target is delay column. So I dropped any rows with nulls in these columns and split the data between 80 to 20 ratio, training set and test set. And the output shows sample counts and the class balance between delayed and on-time flights. So I trained a pipeline by calling a pipeline fit here. On the training data frame, then Spark distributes the computation across all available cores. This is where the power of Spark machine learning lib is demonstrated. So it can scale the same pipeline to billions of records on a multi-node cluster without change in single line of code. And then it comes to the evaluation part. So this is the result. The rock curve having 0.9, accuracy also having 0.93. So this one is a good sign. Then this is the confusion matrix. So I converted the Spark prediction to pandas and use scikit-learn to plot the confusion matrix. Then the feature importance part. The horizontal bar chart shows the importance co-assigned to each feature by the trained random forest model. So departure delay is by far the strong predictor. So this is my Spark analytic. Here I registered the clean flight data frame as a temporary SQL view and wrote a Spark SQL code using common table expression with window function. Then the query calculates each airline's delay rate per year and then use dense rank. Then partition by year to rank airline from best to worst punctuality within the each year. So this demonstrates advanced Spark SQL capabilities on large data set. And the second one use the lag window function to compare each month average delay against the previous month. So this is classic time series pattern in SQL Analytics, and this also runs efficiently on Spark distributed engine on very large data sets. So here I visualized month over month query result as a line chart spanning all 60 months from 2019 to 2023. So in COVID-19 lockdown, this show clear dip in average delays due to dramatically reduced flight volume. So, point. And these are the key findings. So to wrap up, I highlighted the key findings from the analysis. Temporal patterns dominate flight delays. Summer and December are consistently the worst periods, and delays compound throughout the day. And the COVID-19 impacts in 2020 is clearly visible in both volume and cancellation data. So also carrier and late aircraft delays account for the majority of delay minutes, pointing to systematic operational issues. And the random forest model archives strong predictive performance, within departure delay being the single most important feature. In terms of limitation, this notebook uses 3 million rows sampler rather than full 29 million row data set, and collab simulate Spark locally on a single node rather than through distributed cluster. So possible improvements including integrating the weather data from the same areas, applying time series forecasting, and then deploying on a proper multi-node cluster, something like Databricks. So that concludes the walkthrough of notebook. Thank you for watching this, madam. I think I have demonstrated the capabilities of Apache Spark. How we can use these things on large data set. Thank you. Have a good day.